Welcome to today's webinar. Today's topic is Capacitors Decoded, a guide to topologies and selection. My name is Misha Piermike. I hold my bachelor's degree in electronics engineering and have worked in engineering, sales, and marketing roles in the capacitor industry for the past 13 years. During this time, I've helped a countless number of engineers specify capacitors for their applications.
And hi, my name is Zachary Kill-Smith, Director of Engineering and Business Development with Quantic Pactron, leading manufacturer of multi-layer polymer film capacitors. I have a background in both mechanical and electrical with power supplies as well. Thanks.
So capacitors are all around us, from smartphones, laptops, and cars, to medical devices, airplanes, and satellites. Capacitors play a critical role in the operation of virtually all the electronics that we use. Every year, more than 1 trillion capacitors are manufactured, accounting for over $35 billion in annual sales as estimated in 2022. Today's webinar will provide an overview or a refresher of what capacitors are, their basic construction by material, and the key types of capacitors that are commonly used today.
There are multiple commercially available capacitor technologies commonly used today. Each type of capacitor has its own applications, its own pros, its own cons. Today, we're going to be discussing those types, what makes them different, and ultimately, how you can select the right capacitor for your specific need.
As many of us likely remember from our electronics intro courses, a capacitor consists of two electrodes or conductors separated by a dielectric. The dielectric material is an insulator. There are many different types of electrodes and dielectrics, each having their own pros and cons. The different combinations of electrodes and dielectrics lead us to have different types of capacitors, such as film, ceramic, tantalum, mica, and etc. Aside from the different materials used for the electrodes, there are also other factors that impact the characteristics of the capacitor, such as the distance between the two electrodes, the surface area of the electrode, and the dielectric constant. Using the equations seen on the slide, we can relate these different characteristics to the actual capacitance rating. And I'll turn it over to Zach to speak more of the various types of commonly used capacitors.
Thanks, Misha. Much like living organisms, capacitors can be divided up into a family tree of sorts. The highest order of this taxonomy, so to speak, would be the fixed versus variable capacitors. Variable capacitors have very specific uses in RF tuning and radio applications, and they won't be covered in this presentation. Of the fixed capacitors, what most people think of as capacitors, our main families include the electrolytic, electrostatic, and double-layer supercapacitors. Electrolytic capacitors utilize a high surface area anode separated by an electrically formed insulation layer along with a conductive electrolyte to effectively create a very large surface, very large plate with a very thin layer of separation. That means high cap density. The anode can consist of sintered porous metal or roughened etched foil. The cathode remains electrically connected to the electrolyte solution. The electrolyte can be an aqueous liquid or a solid conductive material like pressed carbon or more commonly today, conductive polymers. The construction allows for high cap density, but the need for interaction of polarized molecules in that electrolyte solution increases the internal impedances and lowers the frequency response capabilities of the electrolytic capacitor technology. Since metal oxide dielectrics can quickly be broken down by reverse voltages, electrolytics can only be used in DC applications. Aluminum and tantalum are the most commonly used anode metals for electrolytic capacitors due to the dielectric strength of the formed anodized layers. Electrostatic capacitors are a more classical example of a capacitor. They're very simple in theory. They can consist of two or more capacitive plates separated by an insulator or dielectric material. That material is a defining factor of the capacitor type. It can be anything from free air, glass, paper, plastic. These are similar choices to what you have at the checkout line, right? The main classes of electrostatic capacitors used in modern electrical applications today are ceramic and polymer based. Paper and mica and silica still hold some special positions. The relative permeability of that dielectric material we talked about is expressed in the capacitor equation that Misha discussed as the dielectric constant K. That value plays a very large role in the cap density of the capacitor, as evidenced in the equation. The last subset, supercapacitors, they are not pure capacitors. They actually combine a double layer of electrostatic capacitance paired with an electrochemical reaction, similar to what is seen in a rechargeable battery. So the electrochemical reaction results in a pseudocapacitance because the voltage discharge profile mirrors that of a capacitor rather than a battery. Supercapacitors have very low breakdown voltages and are restricted to low voltage applications, typically below 10 volts. The low charge and discharge rates compared to other capacitor technology mean that they're not suitable for many pulse or ripple applications. On this tree, we can also see an anomalous hybrid capacitor. It is actually possible to combine some pseudocapacitive elements with an electrolytic capacitor in some cases, and we'll be going into that a little bit further in the coming slides. Due to the unique properties of capacitor types, the use of the primary classes of capacitors in the circuit remain largely separated, while amongst the subcategories, such as, aluminum and tantalum or ceramic and film, there's a lot of overlap. For example, we can see that supercapacitors are restricted in voltage, but handle some of the largest bulk capacitance needs. Electrostatics are used heavily in circuits for snubbing due to their ability to handle AC currents, higher isolation voltages, and faster frequency responses. Electrolytics have very high capacitance density and can be used for applications like rectified voltage smoothing, bulk energy storage, or bulk capacitance in a power supply input. Many trade-offs exist with each different capacitor subset, such as the relationship between capacitance density and frequency response or stability. Trade-offs with each technology need to be examined very closely to make the proper selection for your application.
So the unique construction of electrolytic capacitors give them some important advantages. As Zach mentioned earlier, they are very energy dense compared to electrostatic capacitors, as they have a very high capacitance to voltage or CV per unit of volume. This characteristic allows them to provide very high capacitance values. So there are three types of electrolytic capacitors: aluminum, tantalum, and niobium. Niobium is a sister metal to tantalum and it's known for being inexpensive, but niobium capacitors have limitations in their voltage limit, along with the fact that they are not as volumetrically efficient as tantalum. In this webinar, we'll be focused on the more commonly used aluminum and tantalum electrolytic capacitors. So let's start with aluminum. Aluminum electrolytic capacitors have an anode that consists of a pure aluminum foil with an etched surface. The etched surface increases the surface area, thus providing more capacitance. During processing, this etched surface aluminum foil forms a thin layer of aluminum oxide. Now, this aluminum oxide is what serves as the dielectric of the capacitor. Now, a second aluminum foil, known as the cathode foil, makes electrical contact with the electrolyte. Separated by a paper to ensure the two foils do not make electrical contact, the two foils are wound together. After processing, the wound capacitor is put into an aluminum case and sealed. Aluminum electrolytic capacitors use a wet or liquid electrolyte, are more common, but some aluminum electrolytic capacitors use a solid electrolyte. The solid electrolytes are known for being more stable as they better maintain their electrical and thermal characteristics over time and are more vibration resistant. But solid aluminum electrolytics are not self-healing, which means they can prematurely short due to a fault or imperfection in the dielectric. In addition, solid aluminum electrolytics do not offer as high of capacitance values. Aluminum electrolytics typically have a capacitance range of zero point 0.1 microfarads to 2.7 farads, and the voltage ratings of 4 volts to 630 volts. And in some unique cases, they can go a little higher. Some applications of aluminum electrolytics include smoothing, filtering in switch mode power supplies, coupling and decoupling, energy storage, timing and delay circuits with a large time constant. Now let's move over to tantalum electrolytic capacitors. So tantalum electrolytics have an anode that consists of a porous tantalum metal. Similar to aluminum electrolytic capacitors, an oxide is formed on the surface of the tantalum anode during processing, which is the dielectric of that capacitor. The dielectric is then surrounded by an electrolyte, which can be liquid or solid, again, similar to that of its aluminum counterpart. The capacitor case and electrolyte together serve as a cathode in tantalum capacitors. Wet tantalum capacitors are self-healing, making them electrically robust. These wet styles are known for their high energy density compared to solid tantalums and aluminum electrolytics. In addition, they offer very low ESR, which allows for larger currents to pass through the capacitor with less heat being generated in the process. So, tantalum capacitors are available in voltage ranges from 2 volts to 500 volts, but however, common ratings fall more in line with a 2.5 to 50 volt range. Common capacitance ratings for tantalum capacitors range from 1 nanofarad to 72 millifarads. However, there are some styles of tantalum capacitors that do offer much higher capacitance ratings, such as hybrid wet tantalum capacitors made by Quantic Evans. Now, these hybrid wet tantalum capacitors use a ruthenium oxide cathode. That ruthenium oxide has a really, really high surface area, which allows them to pack in significantly more capacitance in a volumetrically small space. These capacitors are capable of reaching up to 0.36 farads in a single compact package and a voltage range of 10 to 125 volts. So overall, tantalum capacitors are highly reliable. Due to this, they are used on a variety of applications where performance and quality are critical, particularly in aggressive environments, including defense applications such as naval avionics, medical, and space.
Ceramic capacitors, on the other hand, are well known for fast frequency response, low ESR, and temperature withstanding capabilities. Contrasting to the electrolytics that Misha described, these are, of course, are of the electrostatic category, and are typically used for lower capacitance applications with higher frequency needs. The two main types of ceramic capacitors used today are single layer ceramic, or SLC, and multi-layer ceramic, or MLC. SLC is typically used for higher voltage and through-hole required applications. MLCC is the leading ceramic technology. Most all ceramic capacitor SMD chips are multi-layer ceramic. The multiple layers allow for a smaller footprint on the board, and higher cap density. The surface mount configuration also eliminates any parasitic losses associated with long leads. Um, and surface mounting also allows for, using both sides of the board. The biggest discerning factor of ceramic capacitors besides the mechanical construction would be the dielectric type or class used. Barium titanate is the most common base ceramic, with other ceramic materials that may be added to that to change the properties. Dielectrics used in ceramics are divided into classes based on their behaviors. EIA Class 1 dielectrics are the most stable over temperature and over lifetime, but they have lower dielectric constants, resulting in lower cap density. Class 2 dielectrics, such as X7R, have a higher K value, higher cap density, but are less stable over time and temperature. And they can also be affected by things like electromagnetism, piezo effects from voltage surges, um, and other effects as well, such as temperature. Class 3 dielectrics have even lower stability and tolerances and are used for general purpose, lower cost applications. Other considerations within MLCCs would be the electrode type. Historically, Precious metals or precious metal electrodes were used and offered higher reliability options to general purpose base metal electrodes. They reduced some of the reliability and handling concerns that MLCCs had. They extended the overall usable life of the capacitor, and they were the go-to for high reliability applications, such as mil, aero, and defense. As of today, lots of additional research has been applied to base metal electrode technology, type MLCCs. The reliability has increased significantly with these products, and they actually can now be approved to mil PRF 32535. So that can be now used for military, DLA, and space applications. Plastic film capacitors comprise the rest of the commercially available electrostatic capacitor selection, along with ceramics. Despite the overlap in the applications in the circuit, the two capacitor types, ceramic and plastic, couldn't be more different. While ceramic is rigid, plastic capacitors, even in constructed form, remain somewhat flexible. This property, along with the low crystallization of that dielectric material, makes plastic capacitors very capable at pulse and high ripple current applications, where ceramics can suffer fatigue from piezo effect and from thermal cycling stresses. K values of plastic dielectrics are significantly lower than those of barium titanate-based ceramics, but they make up for it by having thinner dielectric layers, resulting in comparable densities at the end product point. While ceramics have very high melting points, plastics obviously are much less forgiving in general. These fundamental differences make for the unique advantages between film and ceramic. The two main types of plastic capacitors, film foil and metallized film, will be discussed first. Film foil is has the advantage of having a very high pulse capability due to the heavy electrodes. Film foil consists of layers of film and layers of dielectric plastic insulator. Metallized film is more common today, and at the expense of lower DVDT, slightly lower ESR, you can get higher capacitance density and self-healing capabilities. Self-healing occurs when there's a mechanical or voltage inflicted fault within the capacitor. That polymer in the dielectric can actually fuse around that fault and isolate it from the circuit, and the capacitor continues to operate effectively. This is another very unique and great advantage of film capacitors. There are several plastic dielectrics used in film capacitors, as you can see here. Each has its own unique advantages and disadvantages. Polypropylene is the most common dielectric used, and electrically it has great properties. It's ultra low loss, low dissipation factor, low ESR, great for high ripple applications, great for AC applications. The only disadvantage is the temperature range. It has a lower melting point, and it can only be used up to 85 degrees C rated applications typically, sometimes up to 105 degrees C. Therefore, it's usually excluded in most high reliability applications. Polyester is another very popular choice dielectric. Has higher cap density, higher K value, at the expense of being slightly more lossy. But the higher melting point of the polymer and the inverse relationship between dissipation factor and temperature make it a great choice for high ripple current and high temperature, high reliability applications. Polystyrene and polyethylene naphthalate are very high melting point dielectrics that also have very low losses, very low ESR. They are commonly used as chip capacitors. There can be some handling issues with plastic chip capacitors due to the lightweight of the chips, and the high melting point of the plastic used means that there is diminished self-healing capability. The short list of other specialty plastic films used in capacitors each have their own advantages. PTFT, PTFE, or Teflon, for example, is used in the oil and gas industry and can handle up to 200 degrees C. So that's very unique to film capacitors. In addition to the base dielectric selection, film capacitor construction can play a large role in the characteristics and capabilities of capacitors, and there are several. The most common construction is wound. Wound construction allows for radial and axial configurations, has a simplicity in manufacturing process, and allows for some very high voltage ratings due to the margining and termination style. They are by far the most commonly used film capacitors on the market. Stack construction consists of many layers of parallel stacked electrodes as opposed to two continuously wound electrodes, resulting in a structure that's mechanically similar to a multi-layer ceramic. The construction allows for better cancellation of magnetic fields and lower ESL, lower ESR, due to the closeness of the current collectors of the electrodes, and it results in a self-encapsulated or boxed shape, which increases the volumetric efficiency. Although there are serious advantages to this design, there are increased manufacturing complexities and costs, as well as voltage limitations due to the way that the electrodes are terminated, although there are some ways around this. Lastly, TFD, or thin film deposition. This technique consists of depositing layer upon layer of metal electrode followed by plastic dielectric on a large drum, resulting in a large capacitive element that is later cut up, stacked, and leaded. Mechanically, it's a stack construction, you know, but the construction method is different. So this allows for the thinnest possible dielectric layers, sometimes less than 1 micron, and capacitance densities rivaling those around MLCC. This is the newest construction method applied to film capacitor technology, and as the methods are refined, we can expect broader adoption of this technology in the market. Now that we've reviewed some major capacitor technologies, let's take a look at where these capacitors are used in the circuit. A great example of an application that sort of uses multiple different capacitor technologies would be a switching power supply. There's a lot of active components in these circuits and need for capacitance for everything to work smoothly. No pun intended. Now let's take a look. Starting with the input stage, where rectification and filtering would occur on an AC input, we have a need for bulk capacitance for smoothing of the rectified voltage. Also, in many cases, capacitance is used for power holdup. When AC power is disconnected, sometimes power supplies need to continue to provide power to the output, and that is what power holdup requirements are. Electrolytic capacitors are a great choice for this due to their high cap density. Both film and ceramic capacitors can be used in this stage for transient voltage suppression and limiting reflected noise and any EMI-related applications. Additionally, due to their ability to be manufactured as a safety capacitor, that is, a capacitor that fails open, both film and ceramic capacitors can be used for high potential line-to-line or line-to-ground applications. In many commercial applications, a safety certification or recognition from a certified body is required for that, such as a UL recognition or CSA. In the PFC, or power factor corrected stage that we see here, distorted power coming in is corrected to limit parasitic currents. Some lower ESR electrolytics can find their use here with passive correction in an LC filter, for example. Film and ceramic can also be employed here during active filtering for lower power or higher frequency applications. In the chopper part of the circuit, or the PWM section, electrolytic capacitors are often employed as a boost capacitor due to their high density. If temperature or higher switching frequencies are used, tantalum should be considered due to its higher temperature withstanding ability and its lower ESR. As switching frequencies continue to increase in an effort to reduce overall size, weight, and power, and increase power, along with wide bandgap semiconductor applications, there is an increased need to use film and ceramic capacitors for some of these applications, such as boost capacitors. Film and ceramic safety capacitors are also employed across the isolation transformer sometimes as a means of EMI suppression. At the power supply output, electrolytics can be used to further smooth any past input ripple and also switching ripple power for lower frequency drives. They have important uses for power holdup and peak output power applications as well. Film and ceramic, again, have their uses in higher frequency snubbing applications at the output.
Great. So now we'll talk about some capacitor selection criteria. So when choosing a capacitor, there are a number of factors we need to be mindful of. This section here will cover some of the key criteria to consider when making your capacitor choice. So since the pressure is significantly lower at high altitudes or even non-existent in space, non-hermetic capacitors can leak electrolyte, introducing a variety of reliability and safety issues. When designing a piece of equipment for these types of environments, and when specifying a capacitor for these types of environments, hermetic capacitors are often a common requirement. Now, although hermetic is commonly thought of to mean airtight, hermetic really means that gases and moisture cannot penetrate the capacitor and they cannot escape from the capacitor as well. Now, there is a MIL standards, which is MIL standard 202, method 105, condition D, and this specifies a 100,000 foot altitude test. So if a capacitor can meet this test requirement, if that capacitor can pass all the test parameters within this MIL standard, it is considered well suitable for high altitude applications. Now, moving along, shock and vibration is another area of concern. Um, for example, in avionics systems, the electronics on board, which of course include the capacitors, are exposed to vibration, high levels of vibration, particularly in case of, for example, rotary wing aircrafts like helicopters. Today's modern airborne platforms and even space-based platforms introduce a lot of vibration to the individual applications, and the capacitors must be able to withstand some aggressive shock and vibration conditions. Now, going back on MIL Standard 202, there's a variety of shock and vibration conditions that an electronic components must be tested to. So it's always important when choosing a capacitor for an application which has a lot of shock and vibration to get in contact with the capacitor supplier, which MIL standard adheres to. And the supplier will be able to let you know what MIL standards these capacitors are tested to and designed for, and can go from there. Now, moving along to the failure mode is always a good idea to plan for the unknown. So, despite our best efforts as designers, failure happens. Obviously, capacitors can fail, but the way the capacitor fails should be something to keep an eye on. Solid tantalum capacitors are very, very popular and widely used. However, when they fail, they can fail open and catastrophically. And when I say catastrophically, they have the potential to actually catch fire. Other capacitors can swell as they approach the end of their lives. Now, the swelling can and will often impact other subsystems around it, particularly in an application where a lot of electronics are packed closely together. And they could ultimately render that entire subsystem useless. So, as designers, we must be very mindful and understand how the capacitor fails to account for this in the individual design. Moving along to temperature, so different capacitor technologies have different temperature ratings. So it's really important to pay attention to the capacitor's temperature range, safe operating range, during capacitor selection. Some capacitor technologies have significant performance variations as their temperature changes. For example, some capacitors have much lower capacitance ratings at cold temperatures and can lose half or more of their stated rated capacitance at aggressively low temperatures. And these aggressively low temperatures are those commonly seen in high altitudes or space type applications there. So as designers, we must account for the worst case scenario in these low temperature environments as a part of the selection criteria. There are some capacitors, such as the multi-layer polymer film capacitors, as Zach has discussed earlier, that have very stable performance across temperature. And of course, this is based on the unique properties of the materials used to make these types of capacitors. Um, at some extreme temperatures, a capacitor can still work, but we must derate the voltage accordingly. All these factors should be discussed with the capacitor supplier to make sure that the capacitor chosen for the unique application meets the design criteria for derating and performance and everything in between. Moving along to energy density. So the energy density is the amount of energy stored in a capacitor per unit of volume. This is a key component. Uh, as high energy as the higher energy the density, the more volumetrically efficient the capacitor is. The capacitor's energy density is calculated by dividing the energy stored in the capacitor by its volume. Now, like energy density, power density is measured by calculating the energy delivered by the capacitor per unit of time. Some applications are so volumetrically constrained that they can be really sensitive to power density. So designers must confirm that the capacitor can handle the application's required power needs, which is typically done, again, by getting in contact with the manufacturer. You can look on their data sheet or their website, or just contact them directly. Now, once you confirm the power being delivered by the once you confirm the power, you divide that by its volume, thus giving us the power density. The power density of various types of capacitor technologies can vary significantly. One example is our hybrid wet channel capacitors, made by Quantic Evans, have the designation of being the most power dense in the world. And they're often compared to aluminum electrolytics. So this is a really, really important factor to consider to make sure the best and most optimal solution is chosen.
There is a universal demand for electronics to get smaller and smaller over time, as you folks may know, and capacitors are getting smaller as well. In the case of electrostatics, this is being achieved with new dielectrics, thinner layers of that said material. The introduction of wide bandgap semiconductors are further driving demand for higher frequency, lower ESR, and higher voltage electrostatic capacitors as part of the same drive to miniaturization. In the case of electrolytics, particularly wet tantalum capacitors, more consistent grain sizes are being investigated to increase the surface area and effective capacitance density of those capacitors. So very exciting stuff in both fields. Aside from the hard set rules of electrolytics being DC only capacitors and the frequency limitations of capacitor types, nearly every consideration of capacitor selection can be looked at as a trade-off between reliability, size, cost, stability, longevity, and overall performance. Each parameter must be carefully evaluated and weighted by the designer or engineer to determine the most effective solution for their given application.
So capacitors are all around us. And as you can tell by today's presentation, they have a significant impact on many of the electronics that we use and rely on today. During the design phase, ensuring that the best capacitor specified for the unique application makes sure that performance and reliability of the product is optimized in the variety of applications in which they serve. Now we'll turn it over for some questions and answers.
If the maximum working voltage of stacked polymer film capacitor is under 300 volts, how are manufacturers achieving 630 volts and higher ratings?
Okay, I'll take that one. Um, so it's true that, for the most part, the working voltage is restricted to 300 volts. But by doing things like internally serializing the capacitor and special margining patterns, we can actually create lower internal working voltages for each section. So this method is also employed with MLCC capacitors, ceramics. It's very common. When the number of serializations become very large, this is sometimes referred to as a prismatic design. So in the case of film capacitors, stacked film capacitors, The largest commercially available voltage ratings on the market that I'm familiar with are up to 1200 volts DC currently.
Ceramic capacitors, particularly MLCCs, have advanced significantly over the past 20 plus years, replacing film in many applications. Do you expect to see a time where film capacitors are completely replaced by ceramic?
One as well. Um, you're correct. The MLCCs have been replacing films in many applications, but I would never expect plastic film capacitors to be phased out. Their focus is sort of shifting. MLCCs are becoming increasingly more reliable and more favorable for mid voltage, mid cap applications, 35 volts to 100 volts, where they were previously not really considered in high reliability. That was once a place held, firmly by film capacitors. But new applications for board level film capacitors are opening up in areas such as high voltage, much higher voltage applications that are being introduced by wide bandgap semiconductors, high frequency power supplies, new topologies, resonant topologies, wide bandgap circuits again, and other applications too, such as motor drives, electronic motor drives that were previously not electronic. These are requiring board level high voltage film capacitors. So much like the industry is becoming smaller and smaller, our products are becoming smaller and smaller, and the focus of film is shifting, but it's certainly not going away.
What are the main factors to consider when trying to choose between an aluminum and tantalum capacitor?
That's
Oh,
actually a good question. I'll take that one. I almost like to think the other way around. I like to think of starting with the application because once we answer the questions about the application, that will drive us to an answer on which capacitors are right for the application. One factor to consider, of course, is cost. We're always trying to make sure the overall system is as cost efficient as possible. And tantalum capacitors do tend to be a bit more expensive than aluminum capacitors, aluminum electrolytic capacitors. So if it's very cost sensitive, that's one factor that might help the selection criteria. The ruggedness. I earlier on I spoke on a shock and vibration, for example, and reliability. If this is going into an avionics application where reliability is crucial, or a space application, these high rel applications, tantalum capacitors are a bit more robust. Electrically and certainly from a quality slash reliability standpoint. So a piece of commercial electronics might be something that we see at the electronics store. Those are a bit cost sensitive. We always want to, we don't want to spend more than we have to. And quality, while important, is not the same level of quality that you would require, for example, in a spacecraft. The high reliability applications would tend to lean towards tantalum, and these high reliability applications have a little bit more tolerance for a higher priced component. And applications that don't require as high of reliability or are far more cost sensitive, we typically look at aluminum electrolytic options as well. As I discussed previously, tantalum capacitors are a bit more energy dense. They pack more capacitance per unit of volume. So if space is a constraint, if volumetric space is a critical constraint, tantalum capacitors would really be the way to go because an aluminum electrolytic capacitor with comparable electrical characteristics to its tantalum counterpart, that's going to be physically larger. So again, I always start by asking, what does the application need? And once you understand what the application needs from a volumetric space standpoint, from a reliability standpoint, from a cost standpoint, once you answer those questions, then you can back into which capacitor technology would be the right one for you. Please don't hesitate to reach out to Zach and I and our counterpart, Alex, as you see on the screen. We have quite a bit of capacitor experience between the three of us, and we are more than happy to speak through your capacitor challenges. Even if it's a capacitor we don't manufacture, we always welcome those conversations, and we can help you out however we can.